Hello, my name is Ashley, and for my midterm, I'll be talking a little bit about pseudo-steady state approximation, which I'll be referring to as PSSA from now on. So before we begin, here are the many resources that I have used, which I have linked here. You should be able to click on them. And just a quick note, throughout the slides, I have equations that I've screen snipped from this particular resource just so that the text is more easier to read than my handwriting. If not, then I write out it myself. So for the introduction, I will be covering the basics of PSSA, what it exactly is, and what it does. Its relationship with the following things that we have learned so far in lecture, when it'll be appropriate to use the PSSA method, and of course, why it's important. And it is because it is much easier to calculate when using this equation. And at the bottom here, I have a basic equation that I'll be referring to constantly. Um, the concentration of C with its rate law. And this right here is a derivative, which is a good way to represent the PSSA. So in Professor Smith's lecture, we talked about, reaction intermediates, mechanisms, and rate laws, but PSSA was never specifically mentioned, at least not in the slides. So as a quick definition, here it states that the PSSA estimates the overall reaction rate by assuming the intermediate is constant. So in order to understand what this means, let's first summarize a few things. If we are given this following reaction mechanism here, or in other words, sequence of elementary steps, we can write it as follows. And if we are given this, we also know that when A, for example, converts to B, you have a reaction rate, and of course, B to C, a reaction rate of K2. And if we recall, if K1 is much greater than K2, that means that the conversion from A to B is much faster than B to C, and of course, vice versa. Now, usually when we have complex reactions like this, we like to use the PSSA method, but over here, I'm going to be showing you how to um, solve this equation using the kinetic method instead. And so that just basically means we're going to assume that the intermediate B is not in the pseudo-steady state, meaning we're assuming the intermediate is not constant. In order to do this, we first take the derivative of A, which is equal to negative K1, negative because A is being consumed, times a concentration of A. Through manipulation, we get the following equation here. And so once we have this and we try to solve for C, we realize that we don't exactly know what B is, especially since it's not constant. We would then need to solve for B, which is equal to the following. And because we know what A is, we can simply substitute this, do a further writing, and come up with this equation. And then soon after, you can finally come up with the equation for C. Of course, this is very tedious, and with more products, this will be extremely longer. Thus, using the PSSA method, if we take the same equation or same reaction that we have here, like we did in the previous slide, we then can assume that the derivative of B, or the intermediate, is equal to 0. That means that it is constant. And so if we set that equal to what we set it equal to in the previous slide here, we can then take this equation here and take this equation, and we can soon solve for what B is equal to, which is this. And we will be able to substitute this back into the derivative of C, which is equal to as follows, which you can see is much, much simpler than the last equation on the previous slide and much more easier to calculate. Now, onto our example. My example that I have here is about the ozone layer depletion. So the example reads, the ozone layer depletion is the thinning of Earth's protective shield, which ultimately increases UV radiation that cause an increase in skin cancers. The following are elementary reactions that display this phenomenon. Find the rate law of O2. So first, let's write this out in a way that is familiar to us, which is A goes to B, the intermediate, and finally C. So we see that O here, there's an O here and O here. That means the O is the intermediate, so we can write it out as 2O3 gas to oxygen gas, which then converts to 3O2 gas. All right, so first we're going to solve assuming that B is not in a pseudo-steady state. Again, this just simply means that the intermediate is not constant. So in order to do this, we would have to use the entire equations and manipulation that I showed in the previous slide. And to do so, it would be derivative of A. In this case, it would be O3 squared, as the squared comes from this up here, is equal to negative Ki, or sorry, K1 times A, which is, again, just that. And through manipulation, we know that this A here is equal to O3 naught times exponential of negative K1 times T. And then, of course, we then have to solve for B, or then again, oxygen, which is equal to K1 times A, which we know A is this. And I'm going to do a big parentheses here, times E minus K1 T. Oh dear. Okay. And then minus K2, and then B, and that's just oxygen here. And so we then can manipulate this equation so that the B, or just oxygen, is equal to K1 times A naught, which is O3 naught, over K2 minus K1, and this is all multiplied by exponential of negative K1 T minus exponential of negative K2 T, and this would be your B here. But since we are looking for C, we would have to further manipulate this and get this following equation. And this is all multiplied by 1 plus K2 exponential of minus K1T minus K1 exponential minus K2T. And this is all over K minus K1 minus K2. And this, of course, is from the derivative of C equals K2 and then B. And so this would be our final answer. But instead, if we use the PSSA method, it would be much easier. And so we're first assuming the following: B, or in this case, O, is equal to 0. And this, again, is equal to the following here. So we can just say K1 equal to A, or O3 squared minus K2, B, which is O, and we can move this to the other side, and get oxygen is equal to K1 times concentration of O32 over K2. And then simply plugging it back into here, we get this C, or in other words, we can do O2. 3. dt is equal to K2 times B, which in other words is just this. And this whole thing crosses out here, and you're just left with this following equation. And of course, this here is much more complex than this. So in conclusion, this presentation covered what exactly PSSA is, which of course stands for Pseudo-steady State Approximation, what relationships it had with relation mechanisms, intermediates, rate law, and elementary reactions. Of course, why we use it, the conveniences of using it, how it's faster, and of course, when PSSA can be used. And of course, this is how to represent it and what it assumes. So, thank you for listening.